This is the problem we worked in class last week, where we determined an empirical formula based on percents. And there were 3 steps to that problem. First, we assumed 100 grams of the compound, and so if 30.45% of that 100 grams is nitrogen, you'll recall that meant we had 30.45 grams of nitrogen and 69.55 grams of oxygen. The second step in solving this problem was to convert those to moles. We did quite a few calculations like that last week, where we used the molar mass from the periodic table. And then the third step, once we had these moles, we knew we needed a whole number for number of moles, and we could not round both of those down. And so to come up with a whole number, we did step 3, which was ratio to the smallest. So both were divided by the smallest. When we did that, 2.173 divided by 2.173 is 1 nitrogen, and 4.347 divided by 2.173 gave us about 2 oxygens. I think it was 2.000. And so that's how we determined the empirical formula. In order to know a molecular formula, you must be given a molar mass. So we're going to work a new problem now. An unknown hydrocarbon. You guys should be writing this down. Is analyzed and found to be 82.63% carbon and the rest hydrogen. It is also determined that the molar mass, we did molar mass last time, of the compound is 58.14 grams per mole. Determine the molecular formula. Okay, you're given a molar mass, so you can do the molecular formula. Now, first what we want to do, we've got our percent carbon. Let's calculate our percent hydrogen. So 100% minus 82.63 tells us that there's 17.37% hydrogen. So we're still going to do 3 steps. Look at the steps that we used last time. Step 1 was assume 100 grams, okay? Instead of doing that, let's assume we have 1 mole of the compound. So in other words, we don't have 100 grams. If we have 1 mole, we have 58.14 grams. So we can figure out how many grams of hydrogen, because 82.63% of the 58.14 grams per mole will tell us how much of that is carbon, and 0.1737, remember that comes from 100 minus 82.63, 0.1737% of the 58.14 grams is hydrogen. So calculate that. So I've got 48.041 grams of hydrogen. And 10.099 grams of hydrogen. I think I might have said 48.014 grams of hydrogen when I meant carbon. It's really hard to sit home and lecture to yourself. When you guys are listening, you catch those little mistakes I make like that. Okay, so that's step 1. Step 2 it's the same as before. Let's convert those to moles. I encourage you to pause the video and convert it to moles without watching me do it first. We got to remember what we learned last time on convert to moles. So here I go. So I've converted to moles, okay? Look how those are whole numbers. Last time when we did this, I'm gonna jump back to my previous slide. See, we got 2.173 and 4.347. But this time we're getting a pretty solid whole number. So it looks to me like the formula is C4H10, C4H10. You can check that by calculating the molar mass, right? There's 4 carbons, there's 10 hydrogens, a carbon's 12.01, a hydrogen's 1.01. When I do the molar mass, I get 58.14 grams per mole. How does that check that our answer is correct? Because that's the number that we were given in the problem, 58.14. So oftentimes when you're working with a molar mass, you don't have to have that last step of divide by the smallest. And I'll show you guys, and you'll see this when you're working some of your connect problems. Sometimes you still have to divide them out, but you always go back here and you compare your answer to your molar mass in your problem. Okay? Now, let me introduce from here, so you can flow into the next video simpler. A hydrocarbon is a name for a compound containing what 2 elements? Carbon and hydrogen, okay? This is compounds containing carbon and hydrogen is the whole basis for organic chemistry, which some of you guys will get to take. Once you finish your general chemistry 1 and 2 sequence, you'll go on to take organic. Combustion. The next video you're going to watch deals with a combustion analysis. You've heard of combustion, fuel combustion, whether it's for your vehicle, right, burning your fuel, whether it's lighting your grill, whether it's using natural gas to heat your home. We do combustion in the lab when we're lighting a Bunsen burner. So, in combustion, you have some kind of fuel source. The fuel source is typically a compound. It's containing carbons and hydrogens. Sometimes there's other stuff there, but your fuel source is often a hydrocarbon, like methane, for example, or propane, or butane. Okay? In combustion, we're going to set this stuff on fire, right? What does a fire need in order to burn? Needs oxygen. We do that in the lab. Remember, I showed you guys when your Bunsen burner flame is yellow, it means you're not getting enough oxygen in. And so you open up the top of your Bunsen burner to let more oxygen in and get that blue flame. Okay? When you have complete combustion, your products will always be carbon dioxide and water vapor. And we typically put water as a gas because this is burning, so the water is going to be evaporated. And now that's for complete combustion. Y'all know that like burning your fuel for your car, there's byproducts like carbon monoxide, which is very dangerous. You even get that from your grill or whatever. You get just some soot, solid carbon produced, and it's still water. So that's typically when we're doing combustion, if it's burning a candle in our house, right? The lower the candle gets, y'all, in that little glass jar, you get more soot around the candle. That's because the lower it gets, it can't get enough oxygen, and so that soot's just all the carbon that it's producing. But when we look at combustion analysis problems, we're going to be looking at complete combustion. And you could balance this equation depending on what your fuel source is. You can't balance the equation unless you know which fuel you're using.